The Certification 2 flight was the second flight of the new Vulcan launch system. It was our second flight in pursuit of certification with the U.S. Space Force to fly national security space launches. About 25 seconds into flight, we observed a burn through on one of the nozzles of the two solid rocket boosters. The booster continued to function. That condition did continue to degrade, and later in flight we did observe that the exit cone was liberated.
Of all the things on your SRM, the one thing you can afford to lose is a nozzle. What that does to you is it brings your thrust down a little bit, and it brings down the efficiency of the rocket motor. But it doesn't really endanger the rocket motor, or of course in our case the booster that is attached to. So because we had two and we lost a nozzle on one, the thrust was a little asymmetric. The BE-4 liquid rocket engines compensated for that, and we flew all the way to our destination. And in fact, even though we're known for having the most accurate orbital insertions in the world, this insertion was actually our personal best.
An SRB is a solid rocket booster. It's a composite case filled with propellant, and it allows us to get additional thrust on the vehicle.
They each produce about a maximum of 465,000 pounds of thrust and burn for about 90 seconds, after which they are jettisoned and the rocket continues on its journey to orbit.
The unique thing about SRBs, and one of the reasons we use them on our launch vehicles, is it allows us to tailor pick where we're going and be really precise in our orbital insertion without having to have a really large booster, have a lot of excess propellant. You can really get the most bang for your buck with that booster stage by having solid rocket motors and solid rocket boosters. That's why we put them on our launch vehicle.
SRBs are a cheat code in rocket design. Vulcan is a modular rocket, so we can fly with 0, 2, 4, or 6 solids. That's like having 4 different boosters for that rocket, and that greatly expands what we can do and how flexible we are.
GEM stands for Graphite Epoxy Motor. This GEM 63XL motor is the largest monolithic motor in the world that has flown to date. In Bacchus, we do our propellant casting. In Clearfield, we have our cases where they're manufactured. And in Promontory, we produce our nozzles. All of those components come together in an assembly facility at our Bacchus location.
The GEM 63XL is about 72 feet in length from tip to tail. So this motor is massive. So it's very unique in its configuration, but it does support the needs of the launch vehicle and United Launch Alliance with their Vulcan rocket.
GEM 63XL is based on a long line of motors starting back on the caster motors that flew in our early Atlas vehicles. This motor does have a much higher pressure and thrust than something we've flown before.
The fuel for this SRM is literally metal. We burn aluminum. And so this exhaust is super hot, 6,000 degrees Fahrenheit. It's traveling at very, very high velocity, and it is a mixture of hot gas and grit, alumina particles from that combustion process. So very much like sandpaper grit. And what you want to imagine is the most violent sandblaster you've ever seen. Super high velocity, super erosive, super hot. That exhaust can go right through steel.
The GEM 63XL motors use a titanium shell. So to protect that shell, we have carbon composite components in the throat. Because we had a burn through and we know that that titanium melted, obviously one of those carbon composite insulators wasn't working. So we know that we had some sort of failure in one of those insulators, and that's really where our investigation has focused in why one of those would fail. We're looking at everything from design to manufacturing to transportation. Is there any way that it could have been damaged? And how did that heat from inside the motor be able to travel to the shell and create that burn through that we saw in the video? So we're investigating debris, we're investigating flight data. We've recovered the 2 motors from the ocean, both motors that flew on CERT 2, and doing a large forensic investigation to understand what our initiating event was and how it propagated into the full nozzle failure that we saw on CERT 2.
Quite literally, this investigation started right on launch day.
We began to pull data, structural dynamics, dynamic environments, control dynamics, our SRB team. We had all kinds of people get together in a room, pull initial observations and findings and quick data gathering.
We've had the 5th SLS provide volunteering on the ground searches. NASA provided the helicopter for some of our air searches, as well as the Phoenix team on our ocean recovery.
One of the most unique things about this was quite literally the team just came together. You had Northrop on the phone, everybody was ready to support, and we just hit the ground running.
Solving anomalies like this is very difficult. We have a great team, and we're very fortunate with ULA, Northrop Grumman, and all of our other government partners who have really come together to solve this extremely complex problem and put us on a path back to flight.
From literally the day of the launch, we have been pretty focused on a couple of different parts. We could see on the camera that the nozzle had come off pretty early and that we could expect to find some parts of it near the pad. Within a couple of hours, we found the first piece of hardware, which was a section of a part from inside the nozzle.
The ground discoveries were really impactful to the investigation. The team was really resilient to get into the actual outskirts of the swamp and kind of crawl on our hands and knees to find some essential pieces of flight hardware that had fallen back to Slick 41. So when our team actually pulled up on one of the internal throat entry pieces, it provided a huge key to the investigation, and the team was so excited to find it.
And so that allowed us to focus in on that part and the part that is sitting in the rocket motor nozzle just above it that would normally protect that surface.
We've taken all of these debris pieces that we have and we've put them together into what we believe is a reconstructed CAD model. In addition to that, we've spent the last few months looking in the ocean for the SRBs that were jettisoned off of the CERT-2 rocket. Based on the trajectory and performance team's calculations, we were able to get the sonar boats out to the ocean pretty much exactly where they pinpointed them to be, and we found them resting on the ocean floor.
So when we recovered the SRBs, we were actually able to get the 2 units used on the CERT-2 flight. Once we got it safely on the boat, we were able to take it back to shore and get it back to our engineers at the Cape, where we sectioned off pieces of interest and sent them back to Northrop so we could do further evaluation. It was really amazing to look at the difference between the anomalous unit versus the regular unit. The regular unit gives us a really good baseline of what exactly goes on in flight and if those exact features match what we see from the static test results. So with that, we're able to establish a baseline or control of what we see normally in engineering, and then the anomalous motor really gives us feedback on what exactly happened, what pieces were compromised, and what we can piece together to create this whole picture for the investigation.
So one of the things that is important to understand in context is that it normally takes years to dial in the design of a new rocket. That was the experience for Atlas, for Delta, for other rockets that I've been involved with or designed, and basically every other rocket. Vulcan is completely unique in my experience to come through these first 2 tests this clean, requiring only some minor adjustments in the design, and in fact having 2 really perfect missions in terms of the payload.
Our next step in the investigation is to go to Promontory, Utah for the static fire test.
This test will provide an exact replication of the flight environment that our SRBs see, and it will be done in a horizontal configuration, constrained in our test bay, and then provide us the ultimate data and performance measures needed.
Besides a lot of smoke and fire and some really loud noise, we're going to see about 465,000 pounds of thrust coming out of the about 105,000 pounds propellant in the motor. And what we're planning on measuring is a lot of strain data, thermocouple data, accelerometer data, thrust pressure, a lot of the things that are performance parameters that can help us really understand how did the motor actually perform so that we can correlate that to our models to better help with the predictions supporting the return to flight efforts.
So one of the first pieces of data we'll get is the pressure data, and we will be able to verify that that met the required chamber pressure. And then shortly after, you'll be able to do visual inspections of the nozzle. And looking at the nozzle, we can preliminarily see if everything looks as expected.
The other thing we can do is actually dissect the nozzle. It'll be cut in half. We'll be able to measure char depths. We'll be able to see erosion. We'll make sure that everything is as expected, that all those carbon insulators performed as expected, that the steel shell held up as predicted, and all of that is right in front of us, being able to inspect on the ground and make sure that it is fully ready to go.
5, 4, 3, 2, 1.
Wow.